Sure.
I was the one that asked last week, how do you know when it's when you need to use the pointer or the reference to a variable? And I was looking at some of the code that you had online, and so I was, let's see, does that show up for everybody? We had a case on the encoder where it appears as though you were declaring a long p counts. I just was curious why you would declare that in the middle of a chunk of code rather than define it out in the constants beforehand.
Well, if it says p_counts, it is a pointer to a variable. When we talk about variables, we pass by reference, which is we pass their address, or we pass by value, which is we take whatever their value is and we send it to wherever it needs to go. So there's two different things. Sometimes we need to know the address of something so that we can work on it externally. I'd have to look at that code to see what you're referring to specifically. But again, anytime you see in my code p_ and a name, then it's a pointer to it. That's the intention, is it's the address of the variable, not the value of the variable.
I don't know if this shows up too good on the screen.
Hold it really still. Oh, well, that's right. You see where it says long p counts? You see the long in front of the square brackets?
Yeah.
That requires an address. So I'm giving it the address that I want it to update.
Oh, okay. I got you.
So long, that long is a keyword like that with the square brackets allows us to modify any long in the hub. We just need to know which one. P counts is the address we want to update.
Okay, that makes sense.
Now, I did it that way generically. Now, I think I understand, though, the initial part of your other question where you said, why did you do it that way? I made that spin code work like an assembly program would have to work, because the cog does not have direct access to the hub. It has to go through a pointer. So when I was setting up those demos, I made them work similarly.
Oh, okay. It makes complete sense.
Great. Okay, well, let's get started. We got John's time and attention. He's got some wonderful code posted on the forums that a lot of us are already downloading, so you can go ahead and get it while we get him started. Anyway, yeah, today is January 13th. It's 4 p.m. Pacific, and we're on part 4 of the Holiday Spin Toolkit programming series with JonnyMac, and we're using the one-wire temperature sensor today. If you are following the P2 Live forums next week, we'll have on Tuesday at 2 p.m. Pacific, Jim Bagley sharing his Space Invaders game running on an 8080 emulator. It's totally cool. Chip and I have seen it already, and it looks like a lot of fun. If you have the accessory kit, then you'll be able to play the game with an HDMI cable connected to a TV. There are a couple new things on the Parallax site pertaining to the Propeller 2. And there are 2 quick bites. We're seeking feedback on quick bites and the idea, which is discussed quite a bit in the forums. And I will paste a link to these 2 examples right now in the chat. There they are. So you can take a look at that and give us some feedback on those anytime you want. There are a whole bunch more coming. In fact, I even got one today from Carol Moore. Thanks, Carol, if you're out there. It looks good. I'm going to test it and run it. It's an LED matrix IO pin tester.
You're welcome. Don't post it yet, though. I need to send you an updated zip file.
Yeah, you got it. It'll be a draft, and we'll go back and forth. And I'll be muting people, so if you're muted, please don't take offense. Just unmute yourself to say whatever you want. And JonnyMac works for all of us, so we need to keep him employed. And so I'm going to go and make a deposit in the bank of JonnyMac and invite you to do the same. I just posted a link to his payment page if you'd like to do that. And if you can't, that's fine. But if you can, buy him lunch or dinner or pay his rent. John, we're ready.
Myself. Hello, everybody. Yeah, my rent, I live in Los Angeles, so, you know, and if I try to have, if I've missed anybody with a thank you note, those who have contributed to my sushi and coffee fund that Ken calls it, again, thank you very much. It's very kind, those of you that's done that. So today's the final day of the first 4. Ken and I have talked about doing some more of this. If you guys are up for it, I certainly am. Today we're going to talk about another bus topology called one-wire. It's been around for a while. In fact, the basic Stamp 2 P series had one-wire protocol built into it. Chip and Ken's dad, Chuck, loved one-wire stuff. And at the time, I happened to live in Dallas, so I actually got to go over to the labs and talk to their engineers doing this stuff. So I'm going to show you a trick that they showed me that is not in any of their documentation to make more reliable one-wire code. Now, it's built into the driver, so it's already there, but I'll show you something in my diagrams that you don't see in any of theirs. Did everybody get the downloads today? I tried to get it up about 3 o'clock. I tried to give everybody at least an hour to get the code downloaded. Make sure you copy the libraries, because I made an update to the ANSI file, and I may have done a few others plus the new stuff for today. So make sure you copy those into your normal Propeller library so you've got the latest. Okay, and I guess I should go to my screen, right?
Yep, I got the latest, and I got the first one running and IDing my little one-wire temperature sensor.
Excellent. That's what we want. So Roy's shaming you, Ken.
That's normal.
Yeah, I went and grabbed it when he said I can't make it work, and I plugged it in, and it just works.
That's why I try to make my code. Now, I am human, and sometimes there are problems, but I guess not today. We'll get Ken sorted out.
It's ground signal power, Ken.
I got it, but it's not working.
Okay. All right. So yeah, again, we're in our Spin for Beginners series, although I was thinking about this yesterday, and this has been kind of a crash course because we are covering really kind of advanced stuff from the jump. But thankfully, this is a really great crew and everybody understands. So today we're going to be talking about one-wire. One-wire technology is a proprietary thing that was created by a company called Dallas Semiconductor that got folded into Maxim, and I think in 2001. And so anyway, it is, and I don't know exactly the date that it was created. I couldn't find it anywhere. And when I called them and left a message, they called me back and said, our systems are down. We can't answer questions today. So I don't know. It's got to, I'm pretty sure it's the late 90s. So it's been around a little while, at least 20 years, because I found some old BS2P code from 2001 that had Dallas one-wire stuff in it. Now, you remember last week we were talking about I2C, which was a 2-wire bus. Again, it was one of those, we called it an open collector bus. So the way the bus works is you have to have a pull-up to your VCC to make a 1. Now that's, again, a pull-up means it's going to 3.3 volts through a resistor. And you can make a 0 bit on the bus by pulling it low. Either one side or the other does that. So the one-wire bus is similar electrically in that it's a pull-up and a wire that you can pull low, but it's just one wire. And so it's half duplex. Here's that big long mouthful of a sentence, you know, half duplex, open collector, open drain, one wire. Now this is asynchronous. Now the reason it's asynchronous is there's no clock. That is to say, though, the master still controls everything, and you'll see that. But inside one-wire devices and our own code inside the driver, not what we have to do, but inside the driver, there are some really strict timing requirements because of the way the protocol works. So as I said, the master controls the transactions. The slave can tell the master it's busy, but the master has to ask. And we can see that in one of the versions of the temperature code where we can have it just constantly asking for the temperature, but the temperature sensor can say, look, I'm not ready to give you temperature yet. And we can deal with that busy signal. Now, one wire is certainly slower than other topologies, and there's not a lot of devices because it's not kind of an open thing. You can't get one wire devices from everybody like you can I2C. That said, there are some really interesting specialty devices. You see this picture up here, this is called an iButton. It looks like a big, thick coin cell, but it's actually a smart device. Now, there are some interesting specialty devices that are made in the form of iButtons. One of the things about all one-wire devices is that they have a unique 64-bit ID. And there's three parts to that. There's what's called a family code, which is what the device is. On iButton cans, you'll see it printed right there. Then there's a 48-bit serial number, and that's there. And then there's the CRC for the entire thing, and that's the value there. Now, the iButton cans are the only place where you're going to find the serial number printed, which is why one of our first programs reads the serial number out of the device it's connected so we know what it is in case we're dealing with multiple items on a bus. Yeah. Any questions so far? It's pretty easy stuff. In the one-wire transaction regime, there's really only a couple of things we're doing. The master can reset the bus, which alerts the slaves that, hey, I want to talk to somebody. And what it does in that reset is also looks to see if there's any slaves there. So when there is a bus reset, any of the slaves that are connected will assert what's called a presence pulse that lets the master know that there is indeed something out on the bus. Now, the master can write values, either a 0 or 1, to the bus. So we call those write slots. And then when the master has made a request of the slave, it can read bits back, and that happens in a read slot. So there's really only these things we have to do and write packets of code for, and they're actually pretty simple. Now, if you open up a Dallas, a one-wire document. Oh, by the way, I did include in the downloads today, you may have noticed, a tech docs folder and all of the data sheets for what we've used so far. And then there is also one for the temperature sensor we're using today, the DS18B20. So one of the things that if I haven't said before, I'll say it today, and I'll probably say it again, is whenever you're dealing with a new part, the first thing you should do is download the data sheet. Make sure you have it on your system for reference. So here is a reset for a one-wire system. Now, this thick blue line is the master pulling the bus low. The thin gray line here, that's the bus at the normal idle pull-up level. So in a reset, the master pulls the bus low for at least 480 microseconds. So that's about a half a millisecond, and then lets it go. Then what's supposed to happen is around this time frame, the master checks at 550. It looks at the level of the bus to see if anybody is out there. This red line, that is the slave pulling the bus low in what's called a presence pulse. It's an acknowledge that there is somebody on the bus. And then to finish up the reset slot, you're supposed to just leave everything be for at least, this much time, almost a millisecond from start to beginning. So that's the things I just covered are what you'll see in the normal documentation for one-wire stuff. But you notice there's another line right here with an asterisk. This is one of those insider tricks that the Dallas engineers told me about. And what it is, it's a way they do things. You see, what if you don't have a pull-up on your bus? Now, in our code, we're using a software-based pull-up, but what if you had a hardware-based pull-up and you forgot to put the resistor in? Excuse me. pardon me. If that was the case, the bus would never be high, and this presence pulse would be a false positive. So what they do, and suggested others do, is sample the bus right here. So this is about 10 microseconds after you release the bus. It should have gone high again, and look to see what it is there, and then do the normal presence sampling, and then return that 2-bit value. And you can see we do that in the code. Here is a scope trace. So I actually, connected my oscilloscope to my sensor. And so this is the actual sensor that's on my JonnyMac board. And so this first part here, that's the reset pulse. And then here is the presence response. And you'll notice there's a 550 right in there. From this cursor to that cursor is 550. So that's that sample period. But remember, we're also going to sample right here to make sure that we have a good bus, that we don't have a short on the bus or a pull-up is bad or something has gone wrong. Okay, so that's reset. Easy peasy. Here is how we write bits to the bus. It's just you write it and you hold it depending on what it is. A 1-bit, all bits on the one-wire bus are going to be at least 6 microseconds. And so if we pull the bus low for 6 microseconds and then let it go, what's going to happen is that the slave device is going to sample the bus out here somewhere, so it'll be a 1 at that point. Now for a 0 slot, we're going to hold the bus low for at least 60 microseconds. So for sampling out here, we have a 0 bit. Now after we release the bus, the specification says leave the bus alone for 10 microseconds just to make sure that it reestablishes itself to the pull-up. These rise times here are grossly exaggerated. You saw with a reasonable pull-up, they shoot right up. Okay, this is the read slot diagram. So what happens, remember, the master instigates everything. So to start a read slot, the master will pull the bus low for 6 microseconds. When the slave is expecting to write something back, it'll track with that. And what the master is going to do is 15 microseconds after it pulled the bus low here, it's going to sample. So what that is going to do is that lets the slave assert a 0 or a 1. In this case, it would be a 0. If the slave didn't pull the bus low for the read slot, it would be a 1. And that's how it writes back a 1, is by doing nothing. The pull-up has already established the 1. Okay, any questions? All right, this might be a little tricky to see, so I'll zoom in, but this is a one-wire transaction, again, with my sensor, and with the program that we're gonna run. Now, if we look in here, here is the reset, and here's the presence, which says true, because there is a presence pulse right there. And now in the program, what it does is it does a reset just to see if anything's there. That's what this reset is. Then we're going to ask it for its serial number. So that situation starts off with another reset. There it is. And then we're going to write hex 33 to the bus. That's the command to the one-wire device to dump the contents of its serial number. Now, for this command, you can only have one device hooked up to the bus. If you have more than one device hooked up and you say, give me your ROM, they're going to step on each other. So you don't want to do that. But if you look, then, you know, here is, this is the serial number of my device. Now, the serial number is kind of like in that one-wire thing. On the extreme right is the family code. So for the DS18B20, it has a family code, that's what this last byte is called, of 28. The middle 6 bytes are its unique serial number, and then the first byte is the CRC of the other 7 bytes. And there we are. Whoops, I screwed up my diagram. Anyway, if you haven't hooked up your one-wire device, here's how. I'm sorry I don't have my full JonnyMac graphic done yet, but this should show you how I've got mine hooked up. So the little package, this is called a TO92 for those of you that are new to this stuff. It's got 3 legs on it. What you want to do is orient it so that the flat part is pointing at you. And then the left leg goes to ground. In the code, you can always change this, of course. The center leg, which is the data leg, goes to pin 8. I'm using pin 8 in my code. And then the third pin, which is its power supply, goes to V08 here. So that's how we hook up. Remember, we can tell the propeller to add a pull-up, so we don't need to have one externally. If you were using this with a P1, you would connect a 3.3K resistor between the middle and the power supply to add the external pull-up. Okay? Yeah, we're blasting right through this. Let's go do some code.
John, can I ask a question here?
Of course.
When you look for presence and you see the line go low, is there any way to tell whether there's more than one device out there?
No, because they're all of the devices that are on the bus will do their presence at the same time. So you can't do it with just a reset. What you can do is a one-wire search. Now, the one-wire search is really hairy, and I haven't got it sorted out for the propeller yet. The funny thing is I found a basic stamp file that does it. So I did figure this out once, but it's a little on the gnarly side. So maybe I was a little too specific. Reset will not tell you how many devices there are, but there is an algorithm that lets you do a one-wire search that will identify all of the unique devices on the bus. So I am working on that. When I get it done, I'll put it in the forums. So we're going the easy way today. We're just dealing with one device. Or if we wanted to deal with more than one device, we're going to manually grab their serial numbers and then paste that into our code. In fact, for a couple of the programs that you have to do that. So here is if you're looking at demo number 1, because the P2 is so fast, we can actually write the one-wire stuff in Spin. Now, remember first, we need to establish our pin. This code will let us activate a pull-up on the pin. So I have a constant in the program called int pull-up, which means use one inside the propeller. And if we do, we're going to set the pin to this mode, which acts like about a 3.3K pull-up. Now, if we're using an external pull-up, we're going to then do what's called a high float, which means that if we write a high to the pin, it's actually going to float it. And then remember, we have to activate the pull-up here. So even if it's an external, this will activate the pin driver and disconnect. If it's in float mode, it'll use the external pull-up. So down at the bottom are the bits and pieces of the one-wire code. Now, let me suggest this is not the normal way you would write your programs, but this is how I do development. When I'm developing a new driver, I always start in a single file and I develop my object stuff down at the bottom and then call it. I know that I'm going to later call this, OW as an object name, so I can just take that out later. But that prevents naming conflicts. So here we are. If you remember those, in fact, I'll go back to it really quickly. If we go back to the reset is we pull the line low for 480 microseconds. We're going to release it. We're going to wait about 10 microseconds so that we can let the bus get back to idle, and then we're going to sample it to make sure the bus isn't shorted. Then we're going to wait till this point. I think that's another 60 microseconds later. And we're going to sample for the presence pulse, and then we're going to let it finish up. So if you look in the code, it's exactly that. We pull the pin low. We wait 480 microseconds. We release the code, the pin. So that created that front end reset pulse. Here, we're going to wait 10 microseconds just to make sure the bus rises back up to the pull-up. And then we're going to grab a copy of what's on the bus and put it in bit 1 of our result. We're going to wait for the period that is the sampling time of the presence pulse. And then we're going to put that into bit 0 of result. And then we're going to finish out the reset slot with another delay. So what you saw on the diagram is line for line right there. Very, very simple. Okay, I'm going to go down to, do I have, oh, I don't have right bit in here. But you can see it, when we're writing a byte, we're going to write it LSB first. So what I'm going to do is I'm going to loop through each of the bits in this byte. So 0 through 7, that's going to be LSB to MSB. And I'm going to see if it's 1. If it is, then I'm going to have a 6 microsecond pulse. Otherwise, I'm going to have a 60 microsecond pulse. Remember, this is called a ternary operator. It's an easier, a cleaner way for little things like this instead of if then else kind of stuff. And so again, as a reminder, what we're going to do is if it's a 1, we want a 6 microsecond pulse. If it's a 0, we want a 60 microsecond pulse. And we do that, we pull the pin low, we wait, and then we release the bus, and then we let it finish its 70 microsecond slot by subtracting whatever our pulse was from 70. So very simple. We're going to do that for 8 bits. And read is a little more, you can see here we're doing an individual bit, but you can see it here. Again, we're going to read the same way. We're going to read a byte LSB first. So we pull the pin low. Again, this is the master doing this. We wait 6 microseconds, then we release the bus, and then we wait another 9 microseconds because that gets us to that 15 microsecond point. What happens is inside the one-wire device, there's a timer. When it sees the bus go low, depending on what state it's in, it does a timing. So for bit timing, it says, okay, the bus went low, wait 15 microseconds to do whatever needs to be done and make sure it is being done. And so after this, at this point here, we're at 15 microseconds after we pull the bus low, so we can sample the bus. And we're just going to put that into our bit. And then we finish out that slot. Again, it's 70 microseconds. Here's 15, and 55 is 70 microseconds. So there it is, that easy. The reason that I have a write bit, an individual read bit in here is there are times when we're going to put a device into a mode to do something, and then we're going to use read bit to check to see when it's finished. Finally, remember there is the family code, then there is the 6-byte serial number, and then there's a CRC. This is the algorithm for doing the CRC in the one-wire device. I didn't write this, Micah Dowdy did, it works great. And it's that easy. So if we run this program, as I suppose everybody already has, you're going to see something like this. It should come up and it should tell you that it found, this is your serial number. And hopefully you had a good CRC. Here's your device and here's the name. I created a little very simple identification table that's in an object called one-wire devices that has the names for some known devices. There's not that many one-wire devices, so it's not a big problem to do. Did everybody get that to work? Except Ken, I guess. Try another pin, Ken, just move everything.
Yeah, okay, I'll do that.
Yeah,
I think I'm having a Windows problem.
Uh-oh.
When I've gone into the folder and downloaded the zip and uncompressed the zip, but then when I go into the propeller tool, I'm pretty sure that I'm looking in the right place. I've checked it about 5 times, but I don't see the. I have the week 2 and the week 3, and then the one that doesn't have any number, which I guess is week 1, but I don't have week 4 there, so I can't find this code.
It is on the oops,
When you're there, John, grab a copy of that link up top for the chat.
oh, okay. Yeah, it's on the code is on the first page. Let me where's the
You should put a link, John, every time you post something like that. It kind of makes it easier for all of us.
well, you know, there's only so much to do, Carol. There is already a forum thread for this, so it seems
Well, I didn't really
everything
mean
is in
to.
the same place.
Well, my problem was I just flat out forgot since last week where the heck it was till Ken told me. You know, I've been using it up till now and I just flat out forgot to look there.
I can't find chat, Ken.
Oh, okay. It disappears. So
In
go
share
on,
mode, it's kind of weird.
go on the bottom where the control bar is shown, and then
Well, I'm in share mode on my screen, so that's no
We'll get it.
longer there.
you don't even worry about it. I'll go get it.
Okay.
Actually,
Anyway,
go ahead.
the thread that is supporting these meetings, here's the week 4 code right here. So hopefully, I'm not sure who asked the question that was having trouble with the Windows, but it should say week 4 on the end of the file. I did that so that it would be easy to identify.
Yeah, I'm sorry. I didn't mean to hold things up this
No,
much.
you're
I think
okay.
it's a
No.
Windows problem I'm having, and I'll work it out later. So just go on.
Okay, and I did a copy and paste, and I didn't change that there.
And as for me,
Well,
John, it's
hopefully,
very possible I'm in the same situation because I have the first time PST doesn't work properly for me, and I've just tested with other codes. So we won't worry about me right now. I'll get Roy to help me offline.
All right. Okay. Well, that's a tragedy that things are not working.
I'll let you
for
know when I get it sorted out. I think I grabbed some hardware off someone's desk, so that might be part of the issue.
Okay. At any rate, you know, you saw the definition of one wire is actually pretty simple. I mean, the timing is a little on the hairy side, but the P2 is able to handle that. And so as you see, we can actually do it in high level. Now, if you go to the 1A version, it's the same program. It just uses an external library. So I have a one wire library, and my preference for high-speed stuff is to use inline assembly. So for those that are interested in, you know, starting to look at assembly versus spin, those are two things you can compare, because this does exactly what Reset does, just in the assembly level. There is one significant change though, because Chip added so many neat things to the P2. The CRC algorithm is dramatically faster. Even I have an assembly version of this that runs on the P1, but the P2 version is much faster because you'll notice there is a CRC instruction. There's a few inside the P2, so that helps things go really, really fast. But all of these methods correspond to what you saw in spin. There's a one-for-one correspondence. And why did I do this version? Oh, so I did a third version. I'm trying to wonder why. When I was in my prep mode today, I found a bunch of these iButtons. So this version of the program, you don't have to run it, I will, but it runs continuously. And so if I take out my sensor, it says, hey, there's nothing there. Well, I have another 3-wire device that happens to be a 256-bit EEPROM that I found in my parts drawer. And then I also have this iButton adapter. And so when in Dallas Semiconductor was really pushing these fobs with the iButtons on them as security devices. In fact, when I lived in Dallas, the gym where I went to gave me one of these because it's a unique serial number. And these are a little bit harder to clone than, well, in fact, they're really not clonable because these are not readable. The serial number in the iButton is laser etched. So you'd have to rig up some kind of device if you wanted to do a hack. But if I put this on here, then you'll notice, see, it says silicon serial number. So that's all this is just a serial number. But I have some other ones here. This one is a multi-key button. This one is a temperature iButton. I was reading online when I was looking for that date. The Dallas Zoo took one of these things and set it up. You can actually configure this because it's got a power source inside, and this is a temperature data logger, and so it will record. You can set it up to be recording on an interval. So they set it up and they fed it to an elephant so they could monitor. They could look later to see what the temperature was through its digestive system.
So you can swap these things
I have a
hot?
question.
Yes. Go ahead,
So
Roy.
The iButtons, how do you connect them to the P2? I'm looking online and all I can see are like USB adapters.
Well, I have this really old iButton adapter that has an RJ11 connector on the end. I had to run to the hardware store and get a phone jack so I could rig it up to the board.
Okay, so it just has the 3 power, ground, and signal connections
No.
coming out of that RJ11?
Sorry, thank you for bringing that up. No, the iButtons only have 2 connections. They have signal and ground. A lot of one-wire devices do what is called parasitic power. You'll tend to see, and for the newcomers, if I say stiff pull-up, it means it's a low value resistor, so it can provide more current. So with a stiff pull-up, the device will charge itself from the bus. And in fact, that's why there are some restrictions on how fast you can talk to one-wire devices, because you don't want to deplete their internal power. So technically an iButton has 2 wires, signal and ground, and it gets the internal power it takes by charging its supply from the bus pull-up.
So you're allowed to swap these things hot?
Yes,
without
yeah.
having to turn
Again,
off?
if you see this adapter is just a contact plate, there's actually place for 2. So if I put this on, you'll notice how it showed up on my screen.
Yep.
Yeah, and these are for the security things. Again, at the gym where I used to go in Dallas, I had a fob like this, and there was a plate on the door. You know, normally you'd use an RFID, you swipe an RFID or you put it up next to the plate. Well, in this case, you have a little contact pad and you put your iButton on and away you go, because that 8-byte number is unique. Every iButton has a unique serial number.
Hey, John,
Yes, sir.
just a note, in 1996, at the first Java 1 convention,
Mhm.
they were handing out the Java rings. And the Java
Oh.
ring was nothing but an iButton embedded in the ring.
Okay, so this is earlier than I thought. Yeah, there's a picture on the Wikipedia page of that ring.
Yes.
Yeah,
you
it looks like a big, graduation ring, but it has an iButton on it.
Right. And I've seen them on eBay. You can actually buy them off of eBay. But they were using them at the convention center, kind of like you use the conference RFID tags now. You go to a
Yes.
booth, you plug it into the little iButton reader, and it would register who the user was at the booth.
Yes. Yeah, because you have an 8-byte unique number.
Yep.
And they're a little harder to duplicate. With RFID, you know, if you get close enough to an RFID card, you can capture its credentials. I know because I did that at a cybersecurity company. I made a remote reader that you could kind of brush up next to somebody and grab their creds. With the iButton, you have to have physical contact. So it's a little bit more secure, but I think Dallas might have thought, oh, this is going to be a big, cool security thing and everybody's going to want it. But because it was unique to them, you couldn't get iButtons anywhere else. And they were a little costly. It never really took off, I think, the way that they anticipated.
Yeah, I think the problem that we had is the little button reader that you had was really expensive back then. It was hard to get a hold.
Yeah, they were really proud of the product. It's neat, like I said, and again, I go back, our friend Chuck, he loved them and built it into the BS2P. And you know, there are, of course, these temperature sensors, oh, of course, I don't have it right here handy. Well, sorry. The DS1824B is very popular on Amazon as a wired device. So you can get it with a long wire. In fact, I had a couple because I was working on my own sous vide controller. So I had this submersible temperature sensor that could monitor the water and control the heating device. So they're really popular. You know, those devices, but it's beyond, you know, the iButtons. I know they're still available. In fact, the lady that called me from Maxim, who said she couldn't answer any questions, said, well, we've made an update to our website. Okay. So I guess they're still selling them, but they're not quite as popular as I2C.
Hey, John, on the temperature sensor, where is the most sensitive part of the package? Is it on the flat face in the front or at the top? I've been trying to figure that out.
I don't know, to be honest with you. I tend to just grab it with my thumb and finger, the flat face and the back. And, you know, you can see, oh, I don't have the temperature program running yet, but, you know, we can actually do that. If we go to demo 2 that says DS18B20, now we can look at a specific device. So far, we've been talking about just generics of the protocol, but now we can look at how to deal with a specific device, that being the temperature sensor that we have. So we'll run the program and then we'll look at it. And now what this program is doing that you'll see, and then I'll show you, is it's going and it's looking on the bus to see if there's a sensor, to see if there's anything there. If there is, then it sends out a command that says, hey, give me your ROM. And that's what this is. So this, again, is the serial number for my device. Now, this number at the end is what's called the family code. So that's what tells me it's a DS18B20. This is the serial number, and this is the CRC. So that combined is the entire one ID. And we can see this should be activated. I can see the temperature changing now that I grabbed it. Okay, so let's go now look at how the code works, because now we'll see, again, what I'm have asked or suggested, rather, is that when you're doing when you're working with new parts, and you have this as a folder now in your download today. So here's the DS18B20 datasheet. There's a lot of stuff in here we don't worry about, but you know, have it. So here's some of those same explanations of the protocol that I was already showed you. And we'll get into this in just a minute of how the temperature works. But with this, in this particular program, and this is my structure for when I have a single device, but I don't know its serial number, I've created an embedded variable. This could have been a standard array, but that doing it this way lets me change it. I'll show you in a minute. This is where I'm going to store the serial number after I read it. So in the program, we do a reset. And then if the reset is good, then we're going to read the serial number. So let's go look over in that code. So go to the DS18B20 object and scroll down until you find read, whoops. There it is, read SN for read serial number. See, it's not really big. So here, and forgive me, I don't remember who was asking the question earlier, but here again, this is saying, I want to know the address of the array to be updated. So this is an address. So this is a pointer to the serial number. So to read the serial number, and you saw this in that transaction diagram, we're going to reset the bus. We're going to issue the read ROM command, which is hex 33. That's a constant that's in this file. And then we're going to read 8 bytes from the bus, and that will be our serial number. So when we do that, come on. Then the program clears the screen. It tells us the serial number that it found. This shows the serial number. I put a little fancification in there so that if you're running on an ANSI terminal, it will do the serial number in cyan and the family code in yellow. It's monochrome on PST. And then we drop into this loop that will every second update the temperature. So what it's going to do is this method called read TC, which is a temperature in degrees C. Now, this method relies on only one device being on the bus. And you'll see that where here again, every transaction begins with the one-wire reset. And now we're going to write the skip ROM routine. We can do this because we only have one thing connected, and we're just telling it, don't worry, I know it's you. Just take what I give you next. And in that case, it's going to be a temperature conversion command. Now, this is where I was telling you earlier that the device outside can be busy. And what we're going to do is, now that we've told it to convert its temperature, that takes about 250 milliseconds, if I remember correctly. So what we're going to do is, during that time, we're going to be issuing read bit slots. And what will happen is, if we looked at it on a scope, the temperature sensor will be holding the bus load to tell the master it's still working. Once it's done working, it will release that, and we'll read back a 1 using this read bit. After that, all that's doing is telling us, telling the master, okay, I have temperature now. So the master goes through another transaction where it does a reset and a skip ROM, and now it's going to read a couple of values out of the device's RAM. It's called the scratch pad. That's what SPAD is. That constant is for read scratch pad. And we're going to get a 2-byte value, LSB first, that is the temperature in, it's actually in 0.0625 degrees Celsius. So it's a fractional temperature. Now, the other thing too is it's a 16-bit value, but it is signed. So bit 15 is the sign. And we're putting it into a long. Remember, all of our return values in the propeller are longs. So we have to fix the sign bit. And that's what we do here. For those of you that came from the P1, you might remember the double tilde in front of a variable to extend the sign bit from bit 15 out to bit 31. We now have we have this called sign X, which says extend, and we can tell it which bit the sign is in. So if we have an odd device, like I have seen at least one device I was working with had a 24-bit value, and bit 23 was the sign. So we can use this now. So this will extend the sign, and then by multiplying by 625, we get our temperature to, 1/10,000th of a degree units. They're impractical to use, but at least it's not an odd value like the 0.0625. So this is how we read our raw temperature from one device like we have connected. So going back to the demo, will now display it. And what I'm going to do is I want to display in 1/100th degrees. I want to get rid of 2 of those digits. So I'm going to divide by 100. But what this will do, if by adding 50, that will round up from that digit position. So the last digit in our temperature will be rounded. And now remember, this is in degrees C, and I'm using a formatted output. So this gives me this F. I know this is not a floating point number. I'm taking a decimal, I'm taking an integer and I'm treating it like a floating point that has 2 decimal points in it. 2 digits after the decimal point, rather. Now, to convert to Fahrenheit, you probably all know that to convert Celsius to Fahrenheit, it's 9/5 plus 32 degrees. But remember, our temperature value is in 10,000s. So that's why we have these 4 zeros after the 32. That keeps everything nice and orderly. And when we go back, we get a nice display like this. And you can see that it's a little bit, well, it's actually quite comfortable in my office today. It's 76 degrees. Looking at the wall thermometer, it's a little lower on the wall, but I was holding it. That's why it shot up to 86 degrees. But you can see it updates about every second because I've put a wait count in there to run this loop every second. All right, now if we had a problem, so for example, I'll rerun mine, or you can do it on yours too. Just pull the sensor out and rerun the program. And it's going to say no device. The reason for that is when we pull the device out, remember that we're using an internal pull-up in the propeller. So even though we assert a reset pulse, when we're looking for when we're sampling the line, it's always high. So the bus is high, and then there's no presence pulse. So we get a return value of 1/1, which will tell us that there's no device. Now, I will do this. You don't have to, because I don't want anybody to break anything and then blame me. So let me do it on mine. I'm moving the ground wire over into my signal line, and I'll run it again. And now it says bus short. So if there was a bad device or something on the bus and it was pulling low all the time, you would see that. And just to prove that I didn't break my device, I'll put it all back. And everything's happy. Okay, so this is one of the benefits of these open collector buses is you can do fun things like I just did, where I can deliberately short the bus and not hurt anything, because no device, not the propeller nor a possible slave, is going to try to write a high. So if I short the bus low, it doesn't hurt anything. It just interferes with the communications, and you saw it there. Okay. Any questions so far? We're going kind of fast, but this is a smart crew. So again, this is the way that we'll do most things. But let's say you had a terrarium. I'm thinking about getting a terrarium, and I'm going to want to measure temperature through there. So I'll use these sensors on wires. And what if I want to have 3 sensors in there? What I'm going to need to do is address an individual sensor. So what I want you to do, if you haven't run program 2 and you're following along, or run it again, and then copy your serial number. And then in program 3, oh, I already edited mine, and I told you that's mine. What I want you to do is paste in your serial number and then format it like that. So it's 8 hex values.
But is that in going from least significant to most significant?
Technically it is. This is the correct order. Oh, I wonder, hang on. I may have changed things to match Dallas. You know what? Thank you for catching that. I bet I flopped them around. Okay, forgive me. See, I wanted to match what Dallas was doing. I prefer to have the family code first. So thank you for catching that, because in that array, oh no, I take it back. Okay, you're right. I'm using 7 to 0 right here, or 7 to 1. So what you can is you can reverse those, but it's probably just easiest to manually flip them. But yeah, thank you. When you paste in 20, it's 28 is the first one. So reverse them from the display. Again, I like to start with the family code, which technically is, this is the LSB of the device, but on the display that we just saw, it's going MSB to LSB like we would, see it as if it was a 64-bit value.
Should probably add a comment indicating which is least and which is most on here so people won't get confused.
Yeah. Yeah, until about 2 hours ago, I had the display that you saw in the other programs reversed, but I wanted to match the Dallas documentation. So this is the LSB. So you 28. So in fact here, so you would do this. You'd paste in your thing, put the 28 in first, and just go in this order, rearrange them like that with. Put a $sign there for hex and a comma in between each. So when you get that, now when I run this program, it's going to look exactly like the other one, except it's saying using now. This is saying it's talking to this specific device. And it works similarly, except that we've changed the access to the temperature reading. We're using, this is called read TCA, that's read the temperature from a specific address. And then we are passing it the address of the serial number, that's this here. So when we say at SN0, we're passing it, technically we're passing it the hub address of that byte. And in that version of the temperature reading, so here is, we want a pointer to the serial number. After the reset, remember up here we did a skip ROM. Here we're doing what's called a match ROM. So this is saying to the bus, this is who I want to talk to. So we send the match ROM command, which means any device on the bus now listens for the next 8 bytes to compare it to its own serial number. So this is how we can talk to an individual device among many. In fact, so I happen to have a bag of these things. So what I'm going to do is put a, let me look at here's the second one. So if we look at that, where's my, so remember my old serial number, we'll just go, is this. If I do this again, if I run this program again.
So I plugged in my serial number and I got the using.
Good. So that means yours. It was talking to yours. Yeah, yeah. So what I'm going to do though is I'm going to do. Let me learn this. So here's a new serial number. Remember the other one started with 0. So now what I'm going to do is run the second version of this that's looking for this serial number. F9. Oops. F10. F12. And now this is, I was looking for something, right now, there's no way to go ask a device if it's there except through the search algorithm. So this is a little bit of a drag, but here, if I plug in the old one, now it comes back. So I actually have 2 devices plugged into the bus now. So I plugged in the one that I know this serial number for, and now it's reading it. So this is how, and so what we would do is if we were going to do multiple serial numbers, then we would, we make a copy of this and call this SN1. And we would put that serial number here. And then anytime we wanted to address a specific serial number, we would just send it that number. Now, again, I was hoping that in the last couple of days, I could have figured out that search algorithm. I couldn't. It is kind of gnarly. Once I do, I'll post it in the forum, because that would let you set up a one-wire system with unknown serial numbers and go through and grab them out. Again, going with the code, the difference here is that we're sending it a serial number. The master, the P2 is saying, okay, match this serial number. We write the serial number there. The process is the same. We tell it to do a conversion. We're going to wait. That device will hold the bus slow until it's done. We do it all over again. We reset, we send the serial number, and we read the scratch pad. It's identical. The difference is, in this case, we're telling it to match a specific serial number, and we're transmitting the serial number that we want to talk to. So we get the same kind of value back. As you can see, I mean, these are interesting devices, but there's a lot of stuff going on, especially if you have multiple devices on the bus. So it's not terribly fast. Although
John,
you can go long distance with it, yes.
are you allowed to use the fact that the device doesn't go busy as a non-presence?
Say again?
You have the sensor that doesn't match your serial number.
Right.
You tell it to match, you tell it to convert temperature. It won't show you busy because the device isn't there. Are you allowed to use that to bust out of the loop?
That's a good idea, Stephen. I don't know. I've not tried it, but that's a good, you're still sending it a convert temp, but that's fine. What I was hoping that there would be a universal thing that says, hey, are you there, a specific device?
Right.
Because the convert temp only works for temperature sensors. If you have other types of devices, that you'd have to figure out a workaround for that, but that is a good idea.
So there's no standard non-response is what you're telling me.
No.
Okay.
Now, because I think the expectation was you would search the bus, you would know the serial numbers that are available, and then you would deal with them. But it's a search algorithm that's really, it's a mess. You end up having to do, it's this weird binary tree thing. Now, again, I was feeling a little, wacky the other day, because I actually said out loud to myself, you figured this out 20 years ago with a basic stamp. What's the problem? But if you look at the flow chart, that flow chart lends itself to go-tos better than procedural type programming. So, and I did look it up. Maxim has a suggestion in C, but it's really long, and it because of the complications, it gets very wide. And I don't like to write code that way. So I'm trying to, again, I'll wrap my head around it and I'll have it. And I'll put it out into the ecosystem once it's there.
Super quick update over here, John. So
Yes, sir.
first P2 Edge, when I download to RAM, it would work with PST, but it would not work with Flash. And so it may have been a prototype one, but I just went and got a new one out of inventory and everything is good. So
Oh, good. Okay,
I'm
good.
gonna have Chip look at the one that I just pulled out to see if he could do a failure analysis on it.
Okay.
Or do a
I'm
failure
glad
analysis.
you're up and running. But
It's possible the diff switches are just messed up.
that's true too.
They were set the same. I went through all that. But-
Did you toggle the switches and put them the way they need to be? Because
Yeah.
maybe there was just a bad contact inside.
Yeah, there's something wrong maybe under the switches, so we'll find
Okay.
out.
Okay. Well, I'm glad you're up and working, but with a temperature sensor, we can, if we have one, we can use read TC. If we have more than one, we need to go use the other program to grab the serial numbers and put those into our code, and then we use TCA, and then we can do multiple serial numbers. So at some point in my life, when I do get that terrarium set up, I'm going to know the temperature and all the zones in the terrarium by using a one-wire temperature bus. And finally, because we try to link 1 week to the next, program 4 is sticking everything out onto the LCD, or just the temperature. So I guess technically this is a pricey thermometer, but technically what it is, the beginnings of an industrial control system, because you now can measure temperature, you can put it onto an LCD, and you know how to use rotary encoders. So, you know, a challenge that I'll throw out is make a mini AC controller. You know, it doesn't have to hook up to anything, just have it display the temperature, whether it should be turning on the heater or the air conditioner or neither. And now to do that, you're gonna have to have hot and cold set points. But you can do that by pressing a button to go into a menu selection and use the rotary encoder to set the value and then press a button to come back out. So it's not a simple challenge, but it's a worthwhile one. And I'm going to do it. So in the next week or two, you should see my version of that in the forums. All right. Any questions on OneWire? It's pretty straightforward. You just have to go, I go through the data sheet. Now you don't have to go through the basics of the communication. You'll just, you know, look through the commands that, you know, the device needs to send, that you need to send it. And typically the OneWire device is going to send you data back. You just need to know how that's formatted. But that's easily accomplished. You know, the reading of the device is accomplished with the read feature. I mean, it's actually quite easy. You just have to organize your code around what the device wants to do.
John, I ran into the same problem that you did once using these, and it's very difficult to read multiples on a single bus. But the beauty of the propeller chip is that you got 28 or so spare pins, and I just put one device on each pin.
You can do that. Now in the P1, you know, I have to use a cog because of the timing requirements. Now I know there were a couple of people that said, no, you can do it in spin, but it was never reliable. In the P2, you're absolutely right, because it's inline assembly and you can have as many as you want. You know, the propeller, because of the way the compiler works, going to use the same chunk of code. You're just setting up multiple objects, you know, for different pins. The spirit of it, though, is a multi-drop bus. Wow, everybody's quiet today. I feel like I did something wrong.
You know, John, I was reading whenever I was studying the OneWire, like the last gentleman said he was having problems reading multiple devices. One of the application notes says that you can run into that problem with multiple devices. So they actually have a booster circuit that you could build for boosting the 5 volts, because I think they said that was the biggest problem when you're on multiple devices. And it was a little circuit you had that just boosted power on that bus.
Well, if you're doing parasitic, yes. And one of the things that I tend to do is use a stiff pull-up. The stiffer the pull-up, the better. You'll notice in the pull-up options for the object, you can actually, you know, go use the 1.5K. So if you had a longish bus, then that would work better. And now with the parasitic devices too, they can be problematic because remember, they're getting their power from the bus. So there is suggestions from Dallas that if you're using parasitic devices, that you actually output a high on the bus, hoping nothing is trying to pull it low at the time. So that you can charge the parasitic devices, then release that pin and then go back to normal activations. That way you're not limiting the charge current through the pull-up resistor.
Gotcha.
So again, for temperature, it's neato. And I'm a kind of a temperature nut. I don't know why. I'm very sensitive to temperature. I'm always looking at that thermometer over on the wall. And I know what my comfort zone is. I want my apartment to be between 75 and 78 degrees, and nothing outside of that zone makes me happy. That's when I'm indoors. Outdoors, I don't care what the temperature is. So I'm always doing temperature related things, which is why this ended up in the kit.
John,
Yes, ma'am.
I have a funny question. I don't know. It's not about the sensor. When I did the coffee fund thing, it came up to a John Williams.
Well, that's my legal name.
Oh, okay. McPhail's your stage name then.
Yes, because Carol, do you ever see that little movie from the 70s called Star Wars?
Yeah.
The
On
composer's name is,
occasion.
the composer's name is John Williams. Even though it's spelled differently, literally when I became a professional actor, I said to SAG, hey, my name is legally John Williams and I spell it different. They said, we don't care, get a new name. So my grandfather, his name was Ernest John McPhail, and he named me John. And he was a violinist until an industrial accident took some of his fingers and he could no longer play the violin. So he went on to become this amazing guy that did stuff in steel, including just that direction is, well, sorry, if I'm using that background image, that direction is Dodger Stadium. My grandfather built all the steel that went, his team made the steel that went into Dodger Stadium. So he switched from art to building things. But anyway, taking his name was a way to honor him.
Ah, gotcha.
But yeah, I get it all the time, you know, when I'm here, because, you know, I live in Hollywood. You know, people say, oh, just like the composer. Yeah, that's why my SAG card says something else, is kind of my normal response. I should probably just change it legally and be done. But
Don't
thank
get
you,
all
Carol.
those John William residuals.
Yeah, that would be nice. Yeah, that's why, to be honest with you, that's why SAG is very fussy about names, because you know, it's our brand and it also has to do with those other things. So yeah, I'm sure his residual checks are much nicer than mine.
JonnyMac, a comment. I was just looking at Maxim at some of the one-wire devices. It looks like authentication and ID are a big use of a lot of their parts.
Yeah.
Just, you know, asset tracking and giving something a number.
Yeah, because they have that, you know, it's 8 bits. I don't know what, sorry, it's 8 bytes. That's 64 bits. That's a gigantic number. You know, to give some context to that, because Chip and I were talking about this. If you, I think because we have a milliseconds timer it's using that get MS function that's in the P2 now. If we had a 64-bit register and we changed it every millisecond, it would take almost 3,000 years to roll over.
Mm-hmm.
It's a big number.
And it seems like this would be a good alternative to RFID.
Well, it is, because again, you know, it's physical, mechanical, and they have, you know, these iButtons, some of them have smarts in them. Again, they have data logging capability in some of the iButtons. I noticed when I was looking at the list, they even have humidity sensors. I've never seen one, but I'm kind of interested in that now.
Yeah, they have, there's the basic type, which is just the serial number, which can be used for like access keys. They also have one that's a multi-key one, which can be configured for up to 3 different keys. So you can have, like, people can have access to 3 different zones in your.
Got it. That's why. And I have one of those. Remember when I was doing my iButtons, it said multi-key, but I wasn't sure what it meant.
And then they have the temperature one, and the temperature one can be configured to take samples at a periodic rate up to something like 8,000 temperatures. I mean, there's different size buttons for different number of samples, but you configure it and then it'll just take samples every X amount of time and store them, and then you can read out all those samples.
Yeah, I remember, I think their original intent was for shipping companies could chuck them in a package, and then at the end of the line, they could pull them out and look to see what the environment the package was subjected to.
That's right. We actually had a customer who made hardware that went into 40-foot containers and tracked temperature and location with basic stamps using these.
Yeah,
Could
and
use them again
they
now with
also
the
have
vaccine.
memory. They have 3 kinds of memory where you can, they're ROM, where you just read what's in them, the 64-bit value, but they also have EEPROM and NVRAM and double EEPROM versions. The EEPROM one is where you can add keys, but you can only add, right? You're just adding
Right.
more keys.
Yeah, it's a write only or write once, I guess.
And then the ROM one, or the EEPROM and NVRAM ones, they have up to like 64K bit. So 8K bytes of data could be stored in this tiny little button.
Yeah.
Read and write is probably pretty slow, but it's still a lot of data could be stored in there.
Well, and they're tiny packages too, so it's something that, from a security standpoint, is probably useful in many applications.
And like you said earlier, you can't just read them passively. You have to actually physically contact them.
Yeah.
And then some of the models have their keys are hidden behind secure passkeys, so you have to like give it a 64-bit password to then extract the key out, so it has some added security.
It was funny because when I was driving around today, I was thinking, when I worked at the cybersecurity company, because the County of Los Angeles uses the same really kind of low tech RFID card, so we were able to do all kinds of nonsense with those guys and show them how insecure they were. And I thought, what would I do with this? But we did the same, with the readers at our company. We were assigned to DWP, so we were inside a DWP, and we could just run rampant inside their building. So we put little spy devices inside RFID readers that would pick up the RFID codes. And I thought, could I do the same thing here? And I guess technically you could. If you could see the bus, you could watch the transactions and know what's going on. And then, but it would take a special piece of hardware. It's not like you can clone you can clone an RFID card. There's no way to program one of these iButtons. You would have to have, you'd have to make your own kind of thing that was rigged up to a microcontroller that would spoof the serial number that you'd captured. So it's doable, but it's more problematic than the RFID thing, which is probably one of their selling points for security with these things.
Yeah, the main way it would be doable is similar to the way they do like ATM machine sniffers, where you would put a physical device between the reader and them that would pass through, but store the key when it passed through.
Yeah. We had a device. It's an off-the-shelf hacker device that would just connect into there's a 2-wire bus that a lot of the RFID readers use, and it would read and store the IDs, and then you bring a phone near it, and through a Bluetooth connection, it would just dump all of the ID cards. And then we could do the same thing with this, but you'd have to get into the reader. The RFID card readers are really easy to get into, and all of the readers for these things that I've seen in applications are very small and compact, and it might be difficult to hack something into them. So I guess to your point, you'd have to do a cover type device, which may be obvious.
Yeah, the receptacles for these things are tiny little circles.
Yeah.
And it would be somewhat difficult. You'd have to basically build something that would fit over top of it, and so you would tell there's something fit over top of it.
Yes. Yeah. Yeah, interestingly, I was thinking about this last project. If you download it to Flash, we're actually using 3 bus topologies in the program. Now, we haven't talked about SPY. We're going to do that in a future class if people want to keep doing this, because the SPY bus is used by the Flash, and then we have 1-wire bus to talk to the temperature sensor, and then we're using the I2C bus to talk to the display. If we were outputting to the terminal as well, then we would be using yet another bus topology. It's kind of interesting, all these different communication things in one project, but bringing it all together, making things work nicely.
John, should we talk about the plan going forward? And
please do.
I'll get some input. Okay, so John and I chatted yesterday, and he's worked hard on all these objects for 4 weeks, and we have some catch up to do with just posting them and giving him a break. So we thought we would take about a 2-week break, and then we would actually resume. And one of the topics is serial and using the serial driver that John wrote. And we would do that in 2 weeks on a Wednesday. And we would have the regular P2 forum that occurs on Tuesday, that used to be on Wednesday. That would continue to happen on Tuesday. So that's our current plan. And we're seeking really feedback, because we need to know what the community would like from us in this regard, because we're flexible.
So are you officially moving the live forum, the regular live forum, to always be on Tuesdays?
I think so, yeah. It seems like that's working with people.
Okay. You might want to let people know, because some people still think the Wednesday thing is the live forum, even though it's been JonnyMac's class.
Or we could move JonnyMac to Thursday, and we could move the live forum back to Wednesday. So we could discuss that.
Yeah. Thursday won't work for me, though, sadly. We have work meetings on Thursday afternoon.
Yeah, so going forward, we'll figure that out, Roy, so that we can get the maximum attendance. But in terms of more from JonnyMac, we need to hear from the community if there are topics you would like, because he would just continue on the communication protocol and then more spin to programming topics. We'd probably do servos. We've seen requests for MIDI.
CAN bus.
That's a little bit that I have CAN bus hardware, and Parallax is carrying it now too, but you know, it's tricky with having devices. That's not an easy thing on your desk.
You just run a cable to your garage and plug it into your car, right?
Plug in your car.
Yeah.
What are you going to do with the serial driver demo?
Well, remember, you know, what I try to not so subtly sneak into all of these things is not just, hey, here's an object and, you know, put it to use, but I was trying to show you the technology and the signaling behind it, so that if you see it elsewhere, you've heard it in a discussion. So you saw it today, you know what the signals look like on the one-wire bus. You've seen the signals on I2C and the encoders and those things. So I'll show you how the serial protocol works. And then what I was thinking to do now, so I'm going to ask her out loud. I was going to ask Carol if she had a picture of that Robo Magellan project she was doing, because what I'm trying to teach myself processing, and it's much easier to have an actual project than it is just to follow samples in a book. Especially the processing books are kind of targeted at a different audience than me. And so what I was thinking is that I wanted to do a slightly different variation of Carol's project, so that we could have the propeller sending bytes over to spoof the ping sensors that she was using. And then we would have a picture of the robot on the screen, and we could see where it sees.
I'll send you all my code, and for both processing, and I did the original in the Arduino, but I've since then
I don't care about
translating it.
Yeah, I translate Arduino code all day long. It's you
Okay,
know, programming
good.
is programming. It's just different languages. And,
Well, the only important part is to put out the correct serial data stream for processing to pick it up correctly.
yeah, and that's because I actually have your code, Carol. I found it on GitHub. And
Yeah, it's on GitHub.
Yeah, so I found it. But I want to see a picture of the robot, because I want to do something that looks like your robot on the screen. And then, you know, and then have where the pings, you were doing full circles, but we know the ping is looking one direction. So I want to do pie shapes that grow based on how far out they see.
Yeah, on the robot, they were in a sort of C shape. So I had one looking far left, middle left, center.
Okay, I'll
like
just
that.
go with that. Okay, no problem. You don't have to send me anything. I'll do it. But anyway, the idea is to talk from the propeller, like in Carol's project. Now, she was using an Arduino, but it's a microcontroller reading the, you know, the ping sensors and sending the data out to processing. Again, that's happening through a serial link. And what this allows us to do when we do these kinds of things. Now, Chip has done all kinds of really neat, amazing things with the debug stuff. By using processing, you can get a little creative and make custom things. So what I want to do, because you know, you saw like the graphics that I've done, you know, for our presentations, I use a program called Inkscape, which I really like. And it's kind of relaxing at night. You know, here, what I'm working on that I'll share with the community when it's finished.
John, while you fire that up, I'll show a part that they can get for the next class.
Oh yeah, please.
All right. I just pasted a link for this MAC721 LED display, and they're a couple bucks on Amazon. You get 2 for $6.59. We're going to have them in stock on Monday. Not this cheap, obviously, but get one of these. This will be one of the parts we use with John.
That's for SPY.
Yeah, for us, for SPY.
I just ordered those because you shared the link. I didn't know you were going to get them in stock.
Yeah, there's only 7 left in Amazon.
That's because I bought the first 2. Sorry. I have a bad habit of where John makes decisions and I go grab all the hardware, then it's available.
There's only 5 left now.
Going fast. I think
Ken will have a bunch on Monday.
So back to you, John.
Okay.
Well, you were asking about possible demos. I'd be interested in, you know, we have the ability of transferring data between cogs. I'd like to see a demo of one P2 transferring data to another P2.
Okay. Again, we can, in fact, we could do, when we do the serial thing, we'll do that with cogs, but if it's 2 separate propellers, it's the same way. Now, we'll have to do different pins. One of the things that is unique about the P2 is, you know, we have the smart pin serial, and that's a blessing. And then it also creates a restriction, because if we want to use a smart pin as a UART, then it can only do one thing. Whereas it like, for example, in the P1, where we're using a cog to generate, to do our serial, many times, and I don't know if I talked about this before, but so the Pixie Cam, you know, that Ken really likes to play with. When Ken first called me up and he said, "Hey, I'm struggling with this. Can you give me a hand?" I said, "Yeah, sure." But I didn't have one with me, and he, you know, I was going to be a couple of days before I got it. But what I did was I went to the PixieCam website and I looked at their protocol, and I created a background cog that had, you know, that instantiated serial, and put it on 2 pins. The foreground cog had its own serial, and the pins were flipped. So one's transmit connected to the other's receive. So let's say, for example, I was using pin 15 and 16. In one cog, 15 was transmit. In the other cog, 15 was receive. So I could talk between the cogs directly through the 2 pins. You can do that if you're using software serial. You can't do that if you're using smart pins, because the smart pins exist in the pin and not within the cog. I hope that makes sense. And you can see that if you know, for those of you that are starting to look at smart pins, the full duplex serial object that I use in the P2, the spin cog sets up the smart pin, and then a background cog deals with sending it information or getting information from it. But this is this is a personal project that I'm working on so that I can do better demos or better graphics. Is, again, this is Inkscape. It's a freeware program, and you probably all recognize this. It's not finished yet, but I will release this so that anybody who wants to do presentation stuff can put that together. So this is a 1-to-1 of the JonnyMac, and that's you know, thank you. It's you know.
I was hoping you would release that because I wanted to be able to use it.
Well, yeah, you can absolutely. Let me finish it up, and then I'll leave. And then what I'm doing too is any little parts that I have on my desk that are in kits. I just recently wrote a driver for the DH22. I have a DH11 now, a DHT11 that I need to test with it. But yeah, I grab
Nice.
caliper and the parts and I measure them. And so this is all one-to-one. And for me, this is my after dinner, before bed kind of relaxing thing. I find this very relaxing to create these and then they're useful if I'm planning another article for nuts and bolts on the P2. And then if we're doing presentations and we're helping each other, then, you know, we can do these things. So that's what I obviously use this or parts of it for the diagram that I included today.
And
But
if
Inkscape is,
I had one bit of feedback for you, Johnny, or
Yes, sir.
Johnny Mac, on the week 3, I think it was.
mhm.
You had the extra demo, the 99 quick twist demo spin. The
Yeah.
library file wasn't included in the zip.
Oh, I'm sorry.
I had
Thank
to
you.
I had to go get it off of GitHub. I was just letting you know so you could go fix the zip.
Okay.
But I
well,
did get it working just fine.
Okay, cool. Yeah. That what Roy is talking about is for this little encoder. It's an RGB encoder that uses I2C, so I thank you. I will fix that. I am going to go back through all of the things and kind of backdate everything and make sure that the libraries are updated for every week. So what I'll end up doing is taking the library and the tech documents file and from this week, I will add in the library for this and then put them in all the other weeks just to make sure everything is up to date. Everything is compatible with, now, was anybody on the stream running Flex Prop?
Yes.
Oh, did it work, Dennis? Did you have any problems? I tried a couple of the programs. They seemed to be okay, so I didn't try them all. Did you have any troubles?
Not at all. They all work.
Good. Yeah, good. Yeah, Eric has been very responsive when little gotchas have come up. Well, there's a guy in the forums that wants to do things and so I've said, well, here's the library and spin. So he's using it, but he found a couple of things that are not quite compatible that I'm not going to change. So for those of you that are using Flex Basic, beware, basic keywords might interfere with some things that I use or other people use in their library. So just be wary of that. But anyway, Inkscape is a neat little program. So that's what I'm going to use to draw. I'll draw a funky, cool robot. Maybe I'll watch Mandalorian again and find a cool robot to model and draw it in Inkscape and then have Carol's array of sensors doing its thing.
You need the R2 with the legs and the pole from the boat in the last season.
Oh,
Remember the boat coming out of the tunnel with the R2?
Oh, yeah, in the lava. Yeah.
Yeah.
Hey, John, I just happened to be wearing my related sweater here.
Oh, there you go with Grogu. So those of you that know Rick Gallinson, somebody mentioned the paintball minigun. You know, that was Rick.
Yes.
He's working on that series now. He's working on. For those of you that saw that teaser at the end of season 2 of Mandalorian, he's sitting in that throne from time to time because he's a smart aleck.
Nice. Yeah, they use some really nice new tech things in the Mandalorian. One of the things that I found really interesting is instead of using blue screens and green screens, they have big projection screens and they're projecting the world using Unreal Engine, the Unreal Game Engine, to project the scene around the actors so that they're more immersed in the setting. And it's really, really cool because I think it means much better acting than when against green screen, because acting against green screen is really hard.
It's not fun. I've had to do it a couple of times. It's not fun. The other interesting thing too is they adjust the environment. Rick was telling me he was on they call that set the volume, and he was there one day. It was the episode where Mando delivers the frog lady to her husband on that water planet where all the Mon Calamari are. And he was, so that dock was the physical set, and then it just extended onto the, the walls. And what was going on is before the shoot, they were going along and saying, turn down that street light. So somebody who was running the Unreal Engine had control over that asset and could adjust the brightness of that light as if it was a physical light on a physical set. It was really amazing.
Yeah, they're literally dynamically editing the scene in
Mm-hmm.
Unreal, and it's updating in the world. The other thing that they're doing is that provides an environment lighting onto the actors and the real props in the scene.
Yes.
You wouldn't normally get with CGI. It looks way better doing it that way. The other thing that I really like is that the Razor Crest is mostly done as a practical model effect, using the old school ways that they did in the original Star Wars trilogy.
Well, the upshot of all this is that Jon Favreau is not a kid. He's been around a while, and he knows that story and character matter. So he uses a blend of the best technologies to tell the story. What I was, in fact, when I met with Rick last, I took my P2 and my JonnyMac and over because he had the impression that the Edge was a gigantic card, and I wanted to show him how small it was, because the last assignment he had, last time I spoke with him, was to build a new droid for the Boba Fett show, and I'm trying to get him to look at the P2, because a lot of the things he does are easier to code in the P2 than they are to code in the P1. So I know a couple of the effects guys on the shows. I'm trying to get the P2 involved in there.
Yeah, I agree with you there on that last statement about the P2 versus P1. I'm finding the P2 a lot easier to code, just because the instruction set is so much more powerful, and you can find an instruction to do something that you'd normally have to write a whole function to do.
I'm finding that all the time. You're replacing several lines, especially in the assembly. I think I told this story the other day. In my RGB pixel driver for the P1, there's about 8 or 9 lines of code to swap a couple of bytes inside a given long. That takes one line in the P2. It's amazing. Yeah, it's figuring it out. It's going through and reading through the 350 instructions and trying to figure out, where would I use that? Some of them I know, but I'm hoping that at some point Chip will do a series somewhat like this. It's kind of assembly for beginners, to say, hey, we're going to go through and do small assembly chunks. Stephen and I have talked about this a couple of times. So say, hey, let's, sometimes these bite-sized nuggets are best, and we can find uses, across several applications. But, when you get really experienced, programmers like Chip, I look through the interpreter every day, and I'm still trying to figure out how this skip instruction thing works. I don't quite understand that yet, but someday I will, and hopefully be able to make use of it.
I followed along as he was developing that, and it still bends my brain to try to read through those tables. I understand how it works. Like, I understand the low-level mechanical functioning of it. Yeah. But you still look at this table, there's like 20 instructions, big comment section of like 8 different pathways through the same 20 instructions.
Yeah.
It's like code compression at the maximum level.
It really is. But, because I've seen, people will ask questions, well, how do I do this? Especially, it seems to be coming a bit from the people that are using Flex GUI. They're saying, well, how do I do this in, this happens in Spin. How do I do that in C and FlexProp? Well, I always default to looking inside the interpreter and, following those paths and then pulling those instructions out. The great thing about, even if you use just, the C program is that when, if you use Spin as a test environment, you can test a bit of assembly really easily and then move it over into C.
Yeah, well, you can do the inline assembly in the C code and test.
Oh, yeah, technically
simple
you can.
Little thing. It's really similar to the Spin inline assembly.
Yeah.
It's just compiling it as hub exec instead of native cog code. Although you can do native cog code with other decorations and advanced settings, but.
So Chip, are you going to give us a, PASM 2 for Dummies class?
Yeah, sure. Wait.
Well, I think number 1 needs to be Smart Pins for Dummies with PASM 2 as a side course to that.
Yeah, that'd be fun to do. I'm just working, when you've been going over your thing, John, I've been working on this 8080 emulator, and I'm using, you know, the pattern skipping, and I think it's just like 1.5 pages of code. I've got a little more to write, but I've got it mostly covered, but.
To do an 8080 emulator.
An 8080 emulator, yeah.
In a page and a half of code.
And I didn't know how this thing worked yesterday. I just started looking at the, I got some little stuff off the net. It's an old processor from like 1972, I think.
So to be fair, it's a page and a half of code where it's all skip bytes. So it's, you know, it's really 20 pages of code compressed into a page and a half using the skip mechanism.
Yeah.
But again, this is one of the unique things of the propeller, and maybe this demonstration chip that you're doing will inspire other people to say, you know, for example, the first processor that I ever worked with was called a 1802 in that Cosmac Elf kit. Yeah. And it has kind of a retro resurgence thing going on. I mean, there's a whole Facebook group, and it would be interesting to emulate that in the propeller, because there's all these old school kind of elf video game things that do the same thing that Baggers is doing. In fact, and they're even lower resolution. It's like 64 bits by 30 bits, a really super low resolution video they used to do, you know, back in 1979 when I had my first computer.
Yeah, I think this was from 77, actually. I'm looking at, I got these documents that are like, they look scanned, you know, they're just from 75. So this was from 75.
Yeah. Back in the days when
8080 is an old chip.
Yeah.
46 years ago.
Yeah, in those days there was no PDFs. The manufacturers, like at Toro, we had a full library where every week all of the vendors, Intel and Motorola and all that, they would just bring us new books, and we'd have, you know, shelves and shelves of data sheets in book format that were the thinnest paper. The books were this thick, but the paper was like the worst kind of thin tissue, so they could pack as much into a book, and you go through all those. And it was pretty amazing.
And you have to like you have to have a blank page, a thick piece of paper to put behind every page, otherwise you see through them.
Yes, exactly.
This processor was built, at least by 78, it was built in a 6 micrometer process. I think now we're down to 6 nanometers, less than that even. So that's 1,000,000 times the density. And this whole chip, this whole processor had about 6,000 transistors in it.
Yeah, it's similar-ish to the 6502, which I think actually has less transistors than that even, right?
I don't know. This has some 16-bit operations and some 16-bit memory fetches. So it's kind of
I believe the 6502 is a little bit less in the number, but it's a similar era of technology-wise. You know, the process they use. They literally would use tape on a giant bare floor and scoot around on slippers and knee pads, putting tape down on these giant sheets of paper that they would then photograph to shrink down to be smaller to put them on the chip.
Wow.
Yeah, it was hard.
That's where taping out comes from, is they literally were using actual tape on white paper, black line tape on white paper.
There's so much about technology that we take for granted.
JonnyMac, I want to thank you for everything tonight and the code examples, which will save everybody so much time and frustration in the future and let us do so many cool things. So on behalf of everybody that's quiet too, we thank you.
Thank you. Thank everybody for your patience and interactions. And I'm easy to get a hold of. My email is in the thing. Probably a lot of you have my phone number too. You know, I sincerely enjoy doing what I do, and especially when I can help anybody in the community. I really enjoy that. So thank you all for bearing with me when I'm sometimes unbearable.
Yeah, it was a really good 4-week course, and I'm looking forward to the next steps in a couple weeks.
Ken pointed out a couple of things, but please, if you think, tomorrow you say, geez, I'd really like to know about X, send me a note and, so we can plan something. Because as I was telling Ken, I think I've gotten better by having to force myself to prepare these materials, trying to keep them neat and orderly and do, nice presentations so that they, people can see them later too. But it forces me to really think through things. So, this is good for me. And I enjoy that and appreciate it.
And also, so we can communicate with you effectively. I like to send a lot of email. That's an important part of my job here. So what you do if you don't know how you got here, but you want to keep coming here, go to the link I just pasted in the chat and then go to the bottom of the page and there's a P2 newsletter. And it's just P2 topics. So if you subscribe to that, you'll be notified of everything. And we'll try to give you some advance notice on parts that we might be using. If I can get John to be a couple weeks ahead, really 3 to 4 is ideal, then you'll know what parts you might need for what we're talking about.
Well, that's where it'll be helpful if there's topics that people are interested in, and we can find low-cost parts. A lot of the things we were using is stuff that I already had, and I tend, and I'm sure a lot of people in the group do as well. I see a cheap widget somewhere, and I'll buy it just so that I have it and I can play with it. And a lot of these things, it worked out. What we're trying to do is, again, teach the various kind of connections so that we have the pieces, because the end goal, nothing will make me happier than 3 months from now or 3 days from now, whenever it is, somebody comes back and says, hey, JonnyMac, look what I made. And that's the real joy for me is, with Kevin, the youngster in the group, he's no fear. He tear right into the code and he's making stuff. And that's it. I want to inspire people to be be makers of code. Use the bricks that we put together and make better bricks and share them with the community.
I have a shelf full of boxes with boards, like you said. Oh, this is a neat gadget and it's not that expensive. I'll buy one.
Yeah. Yep.
Ken knows all too well how much I've bought from Parallax, similar kind of thing.
Yeah.
My husband says that I buy boards like other women buy shoes.
I think an interesting P2 forum would be a tour of Roy's garage and all the electronics Roy has, because it must fill half his house. Same for Carol, too. She has the museum in the Northwest.
I think Carol has me beat on electronic stuff, but I may have her beat on pinball machines and trains.
Oh, God, I'm not allowed to buy a train. My husband's forbidden me to ever buy a train kit because he knows how obsessive
They're
I
so
get.
fun.
I love
And
trains.
the new ones you can interface with electronics. Like I'm building a propeller board to talk to the trains via DCC.
Nice.
Everyone else is using Arduino, but I'm going to use a P2.
Yeah, the only trains I'm allowed to have is I have 3 sets of Lego electric trains.
There you go.
Roy, that might be a joint thing we can do together. Now, I'm not a C programmer in that I don't regularly write C code, but I understand C well enough that I translate libraries all the time. The library for, that I left out of the folder for this thing, I tried to go not line by line, but function by function, so that if somebody was coming from the Arduino world to this, but maybe that's something we can do to help other people, because there are people in the Arduino community that I know once they find out what we're doing will be excited about it. And especially when it's so easy and open, what frustrates me when I am dealing with Arduino stuff is I can't just go over to a pane like this and look at a library. It takes a little bit of effort to find the library and weed through it. The other thing too is their ecosystem has become so large that the drivers are very complex because they're trying to write one driver for a multitude of devices. In our world, it's a little simpler and cleaner. And I think from a beginner standpoint, that's helpful, because what I don't want to do, in fact, I have 1 page left. Sorry, Ken, I'm not done with my presentation. I thought I was. I don't want our things to become black boxes. Open the box. So these were my final wrap up is remember for write code, but start with a template. You have that. be consistent with your style, whether it's mine or somebody else's. You know, use appropriate file names. I don't know if it came up yesterday or today. If there was a discussion about, oh, it was Chip yesterday was talking about he had a variable name that was not well named, and it created some consternation for him. It cost him some debugging time.
Yeah, I can back that one up even more. I've been coding for like 30 plus years, almost all of that professionally, and variable naming is like the #1 most important thing you can do for being able to go back to the code years later and read it. And trust me, I've looked at code that I worked on 15 years ago and had to refigure it out. And I thank myself for having done good naming back then, because I beat myself up back then looking at code that was 5 to 10 years older than that I hadn't done that with, and had to basically rewrite it because you can't figure it out without good naming.
Yeah.
One of the things I found to get Arduino users over to propellers, when I started teaching robotics classes for the Seattle Robotics Society and some of the schools, I started with the Arduino version of the Bobot. And then when I moved over to propellers myself, as soon as I started showing people what they could do with cogs rather than what they had on the Arduino, they were sold.
You're absolutely right,
the activity bots.
I've run into that many times in tech conventions, and I'll show people, hey, here's what this really means. Because unfortunately, there's bad information out there. A lot of people don't believe you have 8 individual cogs that are running simultaneously. I had a fight with Nuts and Bolts because their tech editor said, no, it's not really that way. And he published bad information. I was really angry. It's why I walked away from Nuts and Bolts. Because they refused to let me correct that. Now, they did in the last article. You noticed I dinged Nuts and Bolts in that column because they printed bad information. And that was really irritating because it doesn't help this community. But you're right. When you show people, and there I'm going to chime in and ask Ken, another thing for your task list, are we going to have an edge bot? Because it would be really nice to have a board like you did for the microbit that we could plug an edge into. Because with the P2's programming horsepower, man, we could do some really fun stuff.
Let me make sure Roy and Carol will buy enough of them to justify.
Well, I have to wait till COVID's over. I can't teach any classes right now, though I am doing one online for some young men from the Knights of Columbus in Seattle. We'll do Zooms of lessons.
Neat.
Yeah.
One of the things that's also really, really nice about the propeller versus Arduino is that you can often take a project where they needed to use 3 or 4 Arduinos and do it all with one propeller, right? And especially more so with the P2, because every pin can be an analog pin, and a lot of times you're limited by analog inputs on the Arduino because they only have a few. We have 64, right?
Well, now we have real analog output too. I think that the analog out or the analog write function in the Arduino is a PWM output. And it takes a lot of effort to control that frequency. You have to get into the Atmel registers, and it's not clean and easy. I may have told this story, so forgive me if it's a repeat, but I thought it was funny. I was approached by an effects guy to write prop code for, not propeller, but movie prop code for the Star Trek movies. And he was telling me about some of the projects he'd done. In one of the Star Trek movies, it was the new J.J. Abrams Star Trek, when they had Benedict Cumberbatch was playing Khan, and they had him in a prison cell. And in the back of the prison cell is this big red glowy eye thing that was a shout out to 2001, the HAL eye. And inside that, they had 4 boards that had little PIC processors on them running, some version of BASIC. And we had been talking that day about the propeller and the multi-core stuff. And when he told me, I had to put 4 of my boards together to do that prop, I kind of smiled and I said, so you don't have a problem with multi-core, you just do it the hard way. And he laughed and he said, yeah, you're right. And he started, looking at the propeller a little more seriously. So again, we have that opportunity to show people, but I think because there's bad information has got out, and sadly, bad information has a way of sticking. You know, we just have to show people.
I want to redo the sonar array using a propeller.
Yeah, I got to find a ping because I was going to do that as a live demo. So I have to track down a ping. It's in a box somewhere.
I have a few dozen pings. If you don't find one, let me know.
Okay.
Me too. I've got a whole box of them.
That way you can do the thing live. But one of the things that if I can, this is a tiny bit of a complaint. Somebody was whinging in the forums that code that I provided for them because they say, I don't understand what this means. And I pointed out, it's right in the code. It says what's happening. So if you get code from anybody, have a look at it before you run it, because I think most programmers are conscientious enough. They'll tell you what's going on. And, but if you just run it blindly, you know, then you could run into a problem. And again, as I said, I'm going backward now, download the data sheet. If you get a new part, first thing you should download the data sheet, because you have to have that reference. There was a gentleman who called me. He got my phone number and he called me very angry because my one wire object doesn't say that you have to put a pull up on the line. It's in the data sheet. And maybe this is a flaw in me. I don't rewrite the whole data sheet into my code. The idea is we are involved, even as hobbyists, to a degree in some level of engineering, and we have to take responsibility to do that. We have to hook things up correctly, and we have to have the right information, because if programmers, it's like, there used to be this guy who used to write pick books. Every one of his books had about that much of his stuff in it and that much of microchip data sheets. And it was just a waste. And it was irritating. And I'm not that way. In my writing, I will say out loud, go get the manufacturer documentation. You need that along with this. So it's an easy habit to get into, and it'll just save you a lot of headaches later.
Yeah, if you want to be a good coder, you need to take initiative. And part of taking initiative is like going and looking for things that you need without like just going back and saying, oh, this isn't right, to the person that gave it to you, right?
Right.
And especially with your code, you literally can open it and right at the top, it tells you most of what you need to know for how to hook up the hardware. And if it's something complicated, I'm going to definitely go look at the data sheet.
Yeah.
And not rely just on what pins are what, because like you said, there might be a requirement for some external capacitor or resistor or some other thing that you have to do, and the data sheet's going to tell you that.
Exactly.
Yeah,
exactly.
I usually include a link to the data sheet inside my code, and sometimes I even make references to the page numbers in the data sheet.
I do that frequently as well. Sometimes those things move around, and one of the things I'm doing, I'm writing some click objects, and I'm trying to match my methods to their code's function names so that we can help migrate those people too. And so I link into their GitHub, but I am doing more of that, and I will especially do that. I think I did with this guy. In this library, I link directly to their code and saying, hey, this is a spin version of that code. So I'd say out loud, look, that guy wrote the code, I converted it to spin, and I fixed one thing and I added another thing. This is the thing too. Now, I'm human, other programmers are human. I actually found an error in their driver for this device. Now, so I reported it to SparkFun. I said, hey, you have bytes swapped in this thing. Now, they didn't see it because their test code didn't use that feature. And when I try to use it in my code, because I had mimicked theirs very succinctly or accurately, I guess, it didn't work. And I thought, okay, what have I done wrong? And then I looked at their code and it was exactly the same. Then I looked at the data sheet again and I saw, oh, those two registers, they were writing them, big endian, and so therefore so was I. When the registers wanted to be written little endian, once I swapped it around, the feature worked, and I sent them a note. So that's the other thing too. Again, we are a community of makers and users. If you're using code that someone else has written and you find what you believe is an error, and especially if you can demonstrate it so that they can repeat it, report that to them, participate in the process, because that's how we get better libraries as we go. Don't just discard it. Because I think, again, most people that are writing code and putting it out to the world are conscientious. They want it to be good. They want it to be useful for people. So if you find a problem in my code, you guys all know me, tell me or tell the other programmer. And also if you're doing what I was talking about, if you find an Arduino library that changed the spin, give the other person credit too. Don't say you wrote something if it's just a language translation. Give the other person credit because, again, we want to build the esprit de corps, together. We want, no matter what people are using, we're all programmers and we do a unique thing. So let's treat each other kindly.
Yeah, the other good reason for that is that if somebody finds your code and then if you've referenced the original author may have made a newer version of their version that
Right.
might help the person who found your code.
Right.
So if there's cross-referencing, it's really beneficial for everyone, right?
Yes. Yes.
And like you said, it's always good to attribute to original authors because that means that they're more likely, probably, at least for me, I'm more likely to want to contribute more stuff if other people have said, hey, this is good, and Roy did it.
Right.
Right.
Yeah. Yeah. I live in Hollywood. I'm a storyteller. I actually somebody reached out to me one time and said, hey, a buddy of mine wrote a program and I'm having a problem with it. Would you look at it for me? I said, absolutely, send it my way. It was a program that I wrote that had one change in it that broke the program. And I called him up and I said, I found your problem. And he said, really, what is it? And I said, your buddy's a liar. He said, he didn't write that code. I wrote that code and I sent him the original version and I showed him the break. And he contacted me later. He said his friend was a little bit red-faced because all he did was change his name, my name for his. But I have kind of a fingerprint of my style. So that's how I knew it was mine. And then I had the original still on my computer. So be nice to the other people. Give credit where it's due. I don't care if you do that to me, really, but other people, I always try. If I'm using something from somebody else or I'm inspired by somebody else, I'll always credit them in my code so that, as Roy points out, so people can go look at what other contributions that person has made that might be beneficial to them.
So John may not care if you do it to him, but I care if you do it to him because I care if you do it to anyone. Because to me, that's just the wrong thing to do.
Yeah,
agreed. It's good to hear.
I have a question for you, John.
Yes, sure.
For the next demo, you mentioned you're doing serial. Do you have any ideas of what that looks like or what you're planning? Just curious.
Well, I thought I was going to be doing SPI next. Ken decided serial, so that's fine. What I was thinking about for serial, again, I'm gonna do diagrams just like you saw today to show you how serial works, so that you understand what things mean. We throw around the term baud rate, but I bet some people don't know exactly what that means. Or even if they do, how we deal with it. Now we've got smart pins now that act as our UARTs, but before we didn't. And there is still times when a software UART is worthwhile. For example, again, working in entertainment, I do a lot of stuff with DMX. I found it was just cleaner because DMX does this kind of non-standard thing with a pulse before the packet of data that goes out. It was, instead of playing games with the smart pin, it was just easier to do the UART code in software because I'd done it before in the P1 and it's actually much easier in the P2. So we can talk about those kind of things and doing non-standard things. I don't remember what it's called, but there is a 9-bit serial protocol that is used in vending machines because a guy hired me to write a P1 drivers rather a long time ago. To do that. And so if, for example, you got a, you had a situation where you had something non-standard, that's again the goal. I'm trying to teach you a little bit of the underneath so that if you later want to do something standard, like Roy mentioned, he's doing a DCC. I've heard of that. I don't know what that protocol looks like yet, though, but I'm interested in too. I don't have a train yet, but I want one. And of course, if I have a train, I'm going to control it.
Name this
because
I'll send you a train.
well, Ken and trains goes way back when he had these little tiny N-gauge. I think that was what it was, N-gauge, right?
Yeah.
And we had a thing in the office where we could point a TV remote at a basic stamp 2P and it would run a train. And there's another topic is IR remote control. We all have now. Certainly, I don't have one on my
But
desk.
I think
of course,
Roy will have you doing DCC stuff. But
I'd be happy to help him. That would be fun.
It's actually called DCC++.
Oh wow.
And the reason it's called that is because it's an extension of DCC, which is digital command control is what DCC stands for, and it's a protocol defined by the NMRA RI for model railroading, and it's a communication in the track power.
Mm-hmm.
So in order for a microcontroller to communicate it, you actually use a motor controller, and you PWM the motor controller, and the PWMing is issuing data to the decoders via different pulse widths for ones and zeros.
Wow.
Yeah.
That's kind of interesting.
And then you have to, in order to read it, you have to have a circuit that usually uses opto-isolation to get those voltage crossings. It's a differential. So the rails are actually pulsing, plus and minus 5 volts opposite of each other. Sort of like RS-485 almost. But the DCC++ was something that they developed for Arduino land, where you get an Arduino and you plug in a motor shield, and then you download DCC++ software into the Arduino, and you can control your DCC trains and accessories using that hooked up to a computer, and then you're running GMRI software on your computer that talks to that device to run the trains. And they also have a phone app where you can run your trains from the phone app through that whole mechanism connected via your network to the computer.
Neat.
Fun.
Yeah.
Just to clarify, Nicholas, he mentioned serial.
Oh,
You're
yeah.
talking about synchronous serial in 2 weeks, not asynchronous, right?
Oh, wait.
PI.
Yeah, Nicholas, what were you asking about? Because you just said serial. When somebody says serial, I think asynchronous serial, like when we talk to a terminal or something like that.
Well, I saw Ken had the he ordered the 7-segment LEDs.
Yeah, that's SPI.
Oh, that's for SPI. Okay. Because I just happen to be I have some of those similar 7-segment LEDs, and I was working on a project right now trying to drive those, or trying to understand how to. So I was just curious what your setup was going to be, or what configuration or devices you're going to be using.
Well, if you want help now, just reach out in the forums, and I have code to run those things now. That was one of the first things that I did with the P2. And that gave me the opportunity, because those are SPI devices. That's how I made the decision, for example, that my generic SPI driver is in assembly. And now it's inline assembly, so it doesn't take a cog. There are times, though, when if you have really simple requirements for SPI, it's not a generic requirement like you would have in an object, then the smart pins, will blast SPI data all day long. That's how we program the flash so quickly. You have to look into the guts of the P2 loader, but chip sets up a couple of smart pins, and boom, the data goes out to the flash chip in a flash. It's amazing how fast it goes. So we'll talk about those things too, especially as we get into those topologies. So asynchronous serial, like we're talking to a terminal, we can do that in code, or we can do it with a smart pin. synchronous serial, SPI, we can also do that in code or a smart pin. So we'll show different ways to do it. Just as I showed today, we could write one wire code in spin, but it's a little bit more efficient to do it in assembly. Again, the goal is to show you a couple of different, attacks on the same subject so that, it sinks in, because we all have to hear things differently and sometimes multiple times. The goal is you understand it conceptually so that you can apply it. And then later you run into a project or, that's out in the world, somebody has a neat widget and they're doing, again, code for another ecosystem. You say, okay, that's SPI, I know what that means, or that's I2C, I definitely know what that means. And you can apply it. When anytime I've had a sensor and somebody says, here's the Arduino code, it's like, okay, give me some time and I'll translate it. It's a microcontroller. In the end, it's, being cheeky, but it's ones and zeros. We write our high level code a little differently than they do, but in the end, we're still sending and receiving signals to devices.
John, another comment on when we start thinking something like Peter's board, the P2D2, is that what it's called?
Yep.
And he has the Raspberry Pi interface.
I didn't know that.
Now you have two devices that can be SPI, I2C, one wire, anything you want at both ends. And so now you have an opportunity to think both the master and the slave ends, if you will, or that kind of thing, and writing both sides. And so when you're thinking about communicating between the Raspberry Pi and the P2, you get to think about not only talking to a target SPI device, but now you're also on the other side, creating the master SPI device, the same thing with I2C. And so you get to think both ends of the problem in that case.
Yeah. Well, I think
that's
Ray
gonna open
Allen,
up a new opportunity for us to now I'm no longer writing one side.
yeah, sure.
Right.
Yeah, we've been dealing with, simple hardware so that has an established thing, but you're right. I think I mentioned several times I had a P1 project that was actually two P1 pieces. I had a master and a slave device over RS-45. And, as I told my client, because we were both struggling with it, and I said, in the end, we're going to laugh because it'll turn out easy once we understand everything. And what it turned, what ultimately bit me is because we had a very short time frame. That bit of spin code that I showed you for calculating the CRC in one wire, I use that in a lot of communications things because it's reliable. But in the P1 with the packet length we had, it was taking an enormous amount of time and I didn't realize it. I just looked at it and said, oh, I know that works. And once I hooked up a logic, what I ended up doing, this is the other thing I want to inspire you to do. I mentioned this, I think last week, is write test code. A lot of these projects that I've done here, they're little test programs. Experiment. Sorry, I remembered what I wanted. This is my inspirational message for the day. Be like SpaceX. SpaceX blasts off rockets, and if they land and blow up, they don't care. They celebrate because they learned something along the way. Now, you don't want the rocket to blow up, but they're willing to do it. Be willing to experiment, because if you're not, your learning curve will be slower and flatter. You can accelerate your learning curve by experimenting a lot, and that comes with writing little test code. What I ended up doing for my project, because I was really frazzled and didn't know what was going on, and that was a problem. I didn't know what was going on. I hooked up I took another little RS-45 board and I spied on the signal between the two. And I thought, oh, there's my problem right there. Once I fixed that, all the other problems went away. And that was a case where I was writing both ends and I couldn't see where the problem is. So I think Ray Allen actually did a project where he treated a Raspberry Pi as a coprocessor for his P2 to generate video. So he wrote kind of a language that he sent to the Raspberry Pi, and then on the other side, he wrote code that would output video for him and to do graphics primitives. So Ray has gone down that path. I know he's very interested in doing video stuff. He's got lots of interesting things that he's doing now.
It'll be fun to find out. Is that mentioned in the forums or something? Or
Yeah, he's got a whole he's got a whole thread on it where he treated the Raspberry Pi as kind of a graphics coprocessor for his P2, and I believe he's using SPI to send his commands from the P2 over to the Raspberry Pi, and then the Raspberry Pi graphics are going out to the PC. But again,
the SPI interface is by far the fastest interface between.
It's very fast. Yeah, it's very fast. Takes a lot of lines if you're going to do a lot of devices we've talked about. And we'll, at some point, we'll do a big kind of matrix where we say, okay, here are the different things. Here are the pluses and minuses, because I showed you, I don't have it close, but you know, that giant industrial board we did had all kinds of, it had every kind of topology you can think of. I don't think we did one wire, but we definitely had I2C and SPI all over the place on that, because that was the best combination of things. But, you know, going forward, because I know Ken wants to wrap this, let us know what you guys want. And if there's specific topics, if I don't know about something, it may take some time to put together a presentation. And even if I do know about something, it does take time, but because I want these presentations to be worthwhile for you and for me. But do let us know, because we enjoy this.
Thanks again, JonnyMac. And
Okay.
you can start your day job now and I'll do the same.
Yes, exactly. All right, guys.